Hi guys, welcome to the first lesson of higher chemistry. So unit 1, chemical changes in structure. So it's hopefully going to be quite a short wee introduction to one of the trends in the periodic table that we need to be interested in. So what we'll also talk about is periodicity. So that is a term used to talk about the trends in the periodic table, just in case you ever come across that. So the first part is quite straightforward. It is going to be something that's quite new to you. The concept initially can be quite tricky, but hopefully we can break it down enough so that it's relatively straightforward. So we're talking about what covalent radii is. So you might have heard that word radii or radius before in maths, and we're going to be talking about how different elements in different positions in the periodic table, how that affects the covalent radii. Okay, so you need to basically talk about what that is and identify the trends in the periodic table. So that is the whole point of this topic. Okay, so just a wee kind of bit of a background of the periodic table, just to remind you, because you might not have thought about this for a while. So obviously invented by Dmitry Mendeleev, Russian scientist. So back in the day, they didn't really have much information about different elements the way we do now. But back in the day, what he was kind of trying to do is arrange the elements in some kind of order. So he was kind of starting to recognise patterns and things like that within different groups of elements. And so he kind of started putting them into some kind of order. So it's kind of slightly different to the periodic table that we know today. So what he was kind of looking at was like melting point, boiling point, and was looking at atomic mass more than what we look at, which is an order of atomic number. So he kind of had a rough idea about what was going on. So just to show you, so obviously that looks nothing like the periodic table that we know of. So he kind of left gaps, anticipating that there were still elements out there that could fit into this pattern. So completely different to what we're used to. So obviously we're just going to be focusing on what we know about the modern periodic table. So as you know from like first, second, third, fourth year, whenever you've been doing chemistry, the periodic table is obviously arranged in increasing atomic number. So that is still quite important because it actually starts to explain why elements behave the way they do and why particular elements are a certain size, how reactive they are, and stuff like that as well. So as you know, you've got your groups or columns going up and down the way, and your periods going from left to right. Okay, so in the first instance, make sure you get that round the right way. Obviously that is very basic, you spoke about that when you were in first year, but it would surprise you how many people still get that mixed up. So groups are vertical, periods horizontal. So what we're interested in is different trends depending on if you're going up and down a group, and different trends if you're going from left to right on a period as well. Okay. So before we do anything else, there are two things to remember in this topic that will basically allow you to answer any question that is asked about this. So it is quite a long topic. There's a few different trends that we're going to be interested in, but luckily enough, all of the answers are down to these two things, right? So what we've got is this thing that we call nuclear charge, right? So basically that is just how many protons are inside the nucleus, right? So for example, if we have lithium, say, right? So we'll start over here. We've got 3 protons. So again, just make sure you know how to work out your number of protons. So obviously your atomic number tells you that we've got 3 protons. So we've got 3 protons on lithium. If we go to neon, that's got 10 protons. Okay, so what we actually say is that neon is going to have a larger nuclear charge. Okay, so the reason for that is because it's going to have 10 positive charges and lithium's only going to have 3 positive charges. Okay, so basically this neon nucleus is going to have a greater pull on the electrons that are round about that nucleus compared to what lithium would have. Okay, so that's all that means. So we'll talk a bit more about that later. The second thing is the number of filled electrons, right? So, sorry, filled electron shells. So you've already kind of looked at this whenever you maybe were in third year, last year as well, whenever you're kind of drawing your electron arrangements. So that's where page 8 of the data book is still quite helpful. So this page is actually still in the higher data book, right, for obvious reasons, because you do actually need to know how many shells there are in each element, and then obviously how many electrons are in each shell as well. So again, just a wee reminder, just looking down group 1, you can see obviously hydrogen's only got 1 shell, lithium's got 2 shells, sodium's got 3, potassium's got 4, rubidium's got 5, and so on. Okay, so obviously as you're going down the group, the number of shells increases. Okay, so that is very important that you just remember that throughout this entire topic. Okay, so let's have a wee look at covalent radius. So if you're taking notes on this as you're going along, make sure you're kind of splitting up all of the different trends that we're going to look at. So this is number 1. So let's have a look. So basically all covalent radius is how big the atom is, right? So that's it in simple terms. So what you need to recognise at this stage is that atoms don't actually have definite endings or edges. Okay, so up until this point, you would be drawing, say for example, the electron arrangement of lithium, which is 2, 1, right? And you would draw your electrons in, but that is not like a definitive edge of your atom. Okay, so what you need to be able to do is work out bond length, right? So from one atom to another, right, which is this red arrow here. So how we can do that is work out half of the distance of your bond length to get your covalent radius. Okay, so this might actually come up as like a problem solving question or something like that. So say you had 2 iodine atoms joined together, right? So what you can actually do is work out the length of that bond, and then to work out how big that atom actually is, so 1 atom of iodine, all you would need to do is just half that bond length, right? So again, don't worry too much about this just now, because we're going to maybe practice that a wee bit later, but that's just to kind of let you know what it is that we're talking about. Okay, so different elements, depending on where they are in the periodic table, will be different sizes. Okay, so that's what you're interested in the first instance. So let's have a look. So this is actual evidence just to show us what is going on. So straight away that looks quite complicated, but we'll take it a wee bit at a time and just see what is going on. So what we've got, we'll start with this bit here, right? So ideally you would have a periodic table whenever you're looking at this, right? Just so that you can kind of follow whereabouts in the periodic table we're looking at. So what we've actually got is going from lithium across a period over to fluorine, right? So you can see that as you're going along a period, what's actually happening to the size of the atom is that it's getting smaller. Okay, so this on your y-axis is showing you how big that covalent radius is. Okay, so lithium's obviously quite high up, and then as we're going down across our period, fluorine is kind of round about just over 70 picometers, okay, which is obviously a lot smaller. Again, if you kind of look at the rest of them, the general trend is that if you're going across a period, so the next one is your sodium along the period to chlorine, again you can obviously see the decrease, and the same for all of these. Okay, so what you need to be able to do is explain why that is. So, first rule is that if you're increasing the atomic number, so bear in mind that means you're increasing the number of protons, it means the atom is getting smaller. Okay, so that would actually maybe initially go against what you would think. Because surely you would think, right, if we're increasing the amount of stuff that's in that nucleus, surely that means that it's going to get bigger, but it's actually the opposite. Okay, so we'll talk about why that is in a second. So we'll look at the same graph, right? This time we'll look at the group, right? So if we're going from lithium down group 1 to go to sodium, next in group 1 is potassium, and then rubidium, and then cesium. Again, what we're kind of looking at, this is just pure evidence that shows us how we know this, right? So if we're going from lithium to cesium, so down group 1, you can obviously see that the size of the atom is getting bigger. So that's the general trend that's going on, okay? So as you're going down a group, the radius increases. So the further down a group you get, the bigger the atom, okay? So what we're interested in there is our number of shells, okay? So we'll explain these kind of individually just so that they make sense, okay? So just to kind of put that into like a picture, right? So if you're a bit of a visual learner like me and you kind of like visualising what's going on, again, it kind of takes a wee while to get your head around this. So we're starting with lithium on our left-hand side of the period. Okay, so big atom going along, as we're kind of going along and as your atomic number's increasing, that atom's getting smaller. And then as we're going down group 1 and down every group, the atom's getting bigger. Okay, so that is just a way for you to visualise it rather than it being a graph. So this is the bit that you need to make sure that you understand. So this is the kind of higher bit to show your kind of deeper understanding behind that. So you can take a wee note of this as you're going along if you want. I'm going to put the PowerPoints on to Google Classroom and things like that as well, so you can copy them down. But if not, as you're writing as you're going along, that's fine. But this is the kind of bit that you're interested in. So as we're going along a period, our covalent radius, i.e. the size of our atom, is decreasing, right? So the reason for that is because you've got a greater number of protons, which means that you've got a greater nuclear charge, right? So in turn, what you're going to have is a greater pull on those electrons, right? So if we've got, I'll stick with the lithium example and the neon example again. So if we've got lithium, right, we've got 3 protons in the nucleus and we've got 3 electrons, right? So I'll just draw these very roughly so that you can see. Neon, we've got 10 protons, right? And what's actually going to happen is that pull on the 10 electrons is going to be much greater, right? Which means that these electrons are actually going to be much, much closer to the nucleus, right? So that explains why going along a period, as you're increasing the number of protons, your atomic size decreases, okay? So again, we can practice using the nuclear charge rule, but that is basically all it is. So the next part is going down a group. So this maybe would actually be easier to visualise. So as we're going down a group, so say we're going down group 1, the covalent radius increases, so the atom gets bigger, right? So the reason for that is because what we're doing, so if we look at a periodic table, we've actually got an increasing number of electron shells as we're going down our group. So that means that the electrons are getting further away from the nucleus, which means the atom's getting bigger, okay? So if we have, say, lithium again, which has got an electron arrangement of 2, 1, and then if we go to sodium, so we're going down that group, your electron arrangement will be 2, 8, 1. Then if we go down further, we've got potassium, which is 2, 8, 8, 1. So we'll stop there just now. So as you're kind of going down, it's obviously increasing again. So it's slightly easier to visualise. So if you've got 2, 1, and then 2, 8, 1, you're obviously going to need a lot more space the more electrons you've got. So therefore your atom is going to be bigger. Okay, so what we're also talking about here is this thing called shielding effect, right? Which basically means that these outer electrons, so say this wee electron here, your outer electron in sodium, that's actually being shielded from the nuclear pool of the protons in your sodium atom, right? So these shells here are basically protecting it from that nuclear charge from your protons in here, okay? So therefore what we're going to have is like a weaker hold on these outer electrons. So back in National 5, whenever you were talking about bonding and things like that, you know that that sodium atom is quite likely to give that electron away to like a non-metal to form an ionic bond. So that's the reason for that. It's just more weakly held than the other electrons in the atom. Okay, so that is basically it for covalent radius. Okay, so if you want to just take a minute, you can take down a couple of wee notes. As I said, I'll put on the PowerPoint so that you can take notes down at your leisure. I'll also send you links to the BBC Bite Size as well if you want to kind of do a wee bit of extra reading, or if you want to read further on the different trends as well. But we'll stop there just now, and for the next video we'll do a wee quiz on covalent radius just to make sure that we're okay with that and we're up to scratch with that. Okay,